All right. Okay, we're recording. Hello, everyone, and welcome to the QRISE speaker series. Today, we're very honored to be hosting Professor Yongshan Ding to give a talk about his research regarding algorithm-specific quantum error correction. Professor Ding is an assistant professor of computer science at Yale University with a secondary appointment in applied physics. He's a faculty member of the Yale Quantum Institute and is affiliated with the Computer Systems Lab. He is a recipient of the NSF Career Award and the Siebel Scholarship. Professor Ding completed his PhD from the University of Chicago, receiving the William Rainey Harper Dissertation Fellowship, one of Chicago's highest honors. Prior to that, he received his bachelor's in science in computer science and physics from Carnegie Mellon University. Professor Ding is also the lead author of a textbook, Quantum Computer Systems, in Springer Nature's Synthesis Lectures in Quantum Architecture. We hope that your projects are going well as we head into the fourth week of QRISE, and we think that this talk will provide inspiration for your work. Please feel free to put your questions in the chat, and we will address them at the end of the talk. Without further delay, I'd like to give the floor over to Professor Ding. Thanks so much for being with us today.
Thank you very much, Ben, for the kind introduction. Hello, everyone. It's a really pleasure to be here. I'll be discussing some of our recent work from last year, together with how my research has progressed and got here. So I'll motivate some of the computer systems research that I think is crucial for advancing quantum computing going forward. And I hope you will enjoy the line of research that we are focusing on. And potentially having a conversation about working together in the future. So as Ben mentioned, I'll be talking about application-specific quantum error correction, but I'm going to focus on architecture, some ideas of how I think quantum computing research should should involve architecture thinking and some history lessons from building classical computer systems. So this talk will have a combination of algorithm, error correction, and computer systems flavor to I guess introduce such a talk. If there's anything that you feel like I should set up problem more or introduce the background more, let me know. I can always explain on the spot or after the talk. Okay, so this is a joint work with Shifan Shi and Steve Gervin here at Yale, as well as our collaborators from MIT, Hyung-Rak Choi and Dirk England, as well as Fred Trong from Chicago. For full disclosure, I'm a consultant to the Quantum Circuits Inc. Company, which is a spin-off of a superconducting quantum computing hardware company by applied physicists here from Yale. So I'll begin by saying that we really have reached an inflection point for quantum computing, where we're seeing 100 qubit, 1,000 qubit quantum processors actually coming available as test beds for researchers over the last decade or so. The conventional wisdom is that the next challenge is about scaling quantum systems to support more practical applications. And usually people think about scaling quantum systems in terms of increased quality and quantity of the qubits, as we are seeing remarkable progress from these hardware that I'm showing. But my question that I want to throw out there is that is it enough, increasing quality and quantity of qubits? And I think there's a lot to learn from building classical computer systems. Yes, we are building better and more transistors in a processor, but if you look at modern processor today, such as Apple M1 chip, this is already a few years old, but you see uh, 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 a sort of obvious feature is that it has a high heterogeneity. We are seeing processors with regions dedicated for specialized tasks, such as GPUs for graphic processing, neural engine for AI accelerators, and different cores, caches for memory access, etc. We don't know how to build this. We didn't know how to build this heterogeneous chip the first day. This is actually a process how we get here, coined by Ken Iverson, called the processor evolution cycle. So I want to very briefly introduce how classical processor evolution cycle look like and motivate how we should build quantum processors going forward. So first we have some existing processor, let's say some CPU. We identify some bottlenecks in this CPU, commonly some computing intensive tasks. And the next step is to offload some of those tasks from the CPU to some coprocessor units. In history, we have seen floating point of the arithmetic, graphics, I/O, memory access, RAM, offloaded to some other units to address this bottleneck. And going forward, maybe we will learn how to build CPUs better. Sometimes they absorb the functionality of these popular coprocessors, such as the floating point arithmetic are commonly done within the CPU core nowadays. But we're still seeing heterogeneity like GPU and I/O, RAM existing in a chip. So this cycle, I believe, is the motivation for how to scale up a system to serve a larger and larger scale applications. And the central theme of my research is asking the question, will we see a similar Iverson cycle for quantum processors? To answer this question, I want to highlight some of the existing bottleneck in quantum processing. For this talk, if we have time, we'll go through two bottlenecks that I think are limiting the performance of today's quantum processors. The data I/O bottleneck in quantum algorithms. And our solution is to build high-performance quantum random access memory, QRAM in short. And the other is a magic state bottleneck for reaching fault tolerance. And our solution, I call it the magic state functional unit. I'll focus on the first topic, and if we have time, we'll go through some of the earlier work in the second topic as well. The central theme that I guess threads both together is that we want to co-design the application and the compiler software and error correction together to actually reach the performance and the performance requirement of these applications. Okay, so let me introduce the data I/O bottleneck briefly first. So we all know quantum processors have the potential to speed up computation by processing data in superposition and create interference, canceling positive, negative amplitudes, etc. But this speed up will not be practical if the time to encode data into quantum processors will take longer or will dominate the whole process. So encoding data into the quantum processor in the first place, for the quantum processor to process data is a crucial step in reaching so-called quantum speedup. And the role of a quantum random access memory is to speed up this data access time. And to summarize in one sentence, QRAM is really allowing us to encode classical data into superposition uh, rapidly, so that you can use quantum processors to process those data. So encoding data into superposition is a crucial step in algorithm, in many algorithms. One of the examples I can highlight here is for algorithms that include quantum oracles or quantum query algorithms, where oracles should implement access to data in superposition. So the model for a quantum oracle is that you have input quantum signals storing the addresses that you want to query data. For example, you can view this address qubits as a superposition of the indices to a function f that you want to query. That's the input I to the function. And then you want to produce as output the entangled state where the input I is entangled with the output f of I for each I in this superposition. Okay, so in principle, you should be able to access the output of f of I, all of the for all input in superposition. And to view this as a memory access, you can just switch your mental model of this function that you want to compute as some kind of lookup table or memory that you want to access. The input I is the address, and the output f of I is the value stored in the memory cells located at that address. For example, if you want to compute the function XOR function, I can store all the pre-compute the output of the XOR function and write them down in this ordered set in this ordered memory. The goal of a quantum oracle is to allow accessing these memories in superposition. So one way to achieve this is to use multi-control gates. Use quantum control gates where the data is stored in this bus qubit. You will apply gates conditioned on the value in the address qubits, and you do that sequentially for each address. For example, for address 00, I want to write the number 0 because that's the memory value that's stored. So then I want to have this qubit state 0 entangled with the state 00 in the address. And the way I do it is to initialize the bus qubit to 0. And because it's already in the desired state, I don't need to change anything. So this double line here indicate a classical control. I read this value from the memory, it's 0. Then everything in the dashed box here, I don't do. If the value is 1, then I will do the gate. So as an example, for the second gate, I'm going to perform this gate, which is a classical, which is a quantum control gates. The circle control means I only do the gate if the first qubit is 0. and the second qubit is 1. And I'll flip the third qubit so that my result will be state 1 on the bus qubit if my address qubit is in the 0, 1 state, hence performing this entangling operation as desired. So I'm going to go through all the memory cells, performing this classical controlled operation, which is a quantum control gates. And through this process, I can generate this quantum oracle. Okay, so this is the naive implementation of the quantum oracle. But as you see, the number of steps it takes to complete this oracle scales linear to the number of memory cells in the worst case. And if you want to access memory of capital N in size, then potentially you need circuit depth of capital N. This is usually this is related to the performance metric associated with the oracle. So just to introduce some of the terminologies here, the capacity of this memory is denoted as capital N. In this case, we want to access 4 memory cells. The number of address qubits is called the address width. Here is 2. And using n address qubits, you can access 2 to the n memory cells for a Boolean function. And then the data width is 1. We are looking at 1 bus qubit. The output of the function is 1 bit. Circuit depth, as I mentioned, is linear to the memory capacity, capital N. So typically, this is not enough, because if you want to reach quantum speedup, you want to access memory faster than classical individual access can accomplish. So in other words, if your quantum circuit takes time linear to the memory capacity, I might as well just read out all the memory classically 1 by 1, and it will take also linear time. So we want to achieve memory access faster than classical memory access also. I also want to mention later that the fidelity of this query also matters. One way to estimate the fidelity is to count how many error locations in the circuit are there. And in this circuit, if you have a number of address qubits scale as a logarithmic of the capacity, so log of capital N, number of qubits, the circuit depth will be capital N, and the number of error location roughly scale as n log n. And I should really clarify this should be infidelity. So the number of error location is scaled as n log n. Again, this is very bad for large n. So we'll think about how to improve this. This is the data I/O bottleneck. The leading approach is to build this architecture called bucket brigade QRAM. I'm going to very quickly go through this construction of QRAM and then understand what do we need to do to improve the latency and fidelity. Okay, so again, with the query model, QRAM can implement the oracle. QRAM, the elementary unit of building a bucket brigade QRAM, is this quantum router. You can view this quantum router as a 4-qubit quantum circuit, which involve 1 input qubit, 2 output qubits, and 1 for the left output, 1 for the right output. And the gate, there's a router qubit in the middle. And the quantum circuit associated with this router is just 2 control swap gate. This first gate is an empty circle control swap. So if A is 0, I'm going to swap input with the left output. If the router state is 1, I'm going to swap the input B input qubit with the right output qubit. Notice that this is quantum gates, so you can actually perform this swapping operation in superposition if your router qubit A is in a superposition state. So then here, is to understand this quantum router, it's essentially two-step process. One is the routing step. If router state is 0, I route to the left. If router state is 1, I route to the right. There's also the writing process at the end. If the left branch associated with the classical data x0, it's a bit 0 or 1, and the right-hand side is x1, then I will perform x gate if to this output qubit, if x0 is 1, similarly for the right output. Okay, so in other words, you can write to the qubit B in superposition, depending on the value of the classical memory. So to construct a larger scale QRAM or accessing a larger capacity memory, you can then construct this tree structure of routers, and you will just access a memory cell by loading multiple bits of address according to this binary tree. So if the first qubit is 0, I route to the left. The second address is 1, I route to the right. Third qubit is 0, I route to the left. Here you're accessing the 010 entry of the memory. And you can access all memory cell in superposition because everything is constructed with these quantum control swap gates. Notice that the overhead of this is to use number of qubits as proportional to the size of the memory. That's the size of the binary tree. But then the step can be done in parallel for each layer of the tree. So the circuit depth is reduced to logarithmic of n. As I mentioned, it's desired to reach low depth circuit for this memory access. So this is a very brilliant theoretical proposal for accessing memory with a shallow depth circuit. But if you think about practically implementing it, one of the first questions that come into mind is how do you integrate this tree structure in, let's say, 2D nearest neighbor architecture, because that's what most quantum superconducting quantum hardware, for example, is good at. If you are thinking, yes.
Sorry to stop you. I don't know if you see Shantanu has his hand raised.
Oh, okay.
I don't know how you wanted to deal with questions, or I wanted to let you know in case you couldn't see the participant list.
Okay, if it's clarification question, maybe we can answer them right now, or if it's more in-depth question, maybe my later slides will be answering them, so we can wait until afterwards.
Definitely, yeah, I'll wait, sir. Sorry
Okay.
for interrupt.
Good. So as I said, if you want to implement this QRAM architecture on, let's say, superconducting 2D nearest neighbor architecture, what are some of the challenges for demonstrating that? How do you embed this tree structure into 2D? Well, if you had hyperbolic space, then it will be really easy. You just embed it into hyperbolic 2D embedding. But typically, that's really hard to implement in practice. So we can maybe use the Euclidean representation of this embedding of a tree in 2D, such as this fractal style. You can build a larger tree by growing in space outwards. The fundamental issue associated with this is that in order to fit the exponentially growing number of leaf nodes in the space, you will unavoidably increase the spacing between let's say, the root node and the children of the root. You have to stretch them out so that you can fit everything in the, say, lattice, 2D lattice, right? So stretching things, increasing the distance sometimes will slow down your interaction between them. So we set out the project to understand, can you actually implement this in 2D Euclidean space without sacrificing the time for quantum random access. So the idea for embedding tree in 2D, such as this fractal style, is not new. People have done it for VLSI classical circuit synthesis, but also in the first proposal of QRAM, it was also mentioned that H-tree, the fractal style, can be used to embed a tree. But what we noticed is that if you have a large subtree, you unavoidably space the higher level qubits far away. For example, if you have a capacity 16 memory and you want to write them, lay them out in a 2D lattice, maybe it's something like this. And you will see there's a spacing between the qubits that's needed to make everything fit, like such as the green qubits in the middle. But if you look at the spacing scaling, this length, it actually scales linearly or square root of the size of the memory. And if you only have nearest neighbor interactions, let's say you perform 2 qubit gates between them, then interacting this center qubit with this left child will take some time to do, right? So for example, if you have swap operations to interact this orange qubit with the other orange qubit, you have to use a linear depth of swap circuit to do that. Our solution, without inducing this overhead of this latency, is to use teleportation style of circuit with circuit measurement. So if you can generate EPR entangled state for those green qubits, they're not storing any information anyways because they are padding qubits. You can use them to generate the entanglement of their nearest neighbors, and then perform Bell state measurements in also in an interleaved but parallel way. You can swap the entanglement between the remote qubits. In other words, you can accomplish teleportation of the qubit in a long distance with constant depth circuit. For example, with these gates, you only need circuit depth of 4 for arbitrary distance teleportation. So in other words, regardless of how far away these qubits are, for large-scale QRAM, you can still interact them in constant constant time. So this is crucial to the QRAM circuit depth, because if you needed to interact these qubits with scaling linear to the distance of them, then the circuit depth will be a lot longer, and erasing the advantage of a logarithmic depth quantum circuit for QRAM in the first place. Okay, so this is what we developed in this paper published last year. Another concern was that it will inevitably involve many gates, potentially linear to the distance here. So in order to reach high fidelity QRAM, we actually need to think about quantum error correction. Okay, so that leads to my second topic related to QRAM, is how to improve the fidelity of this access. So there was a very interesting work coming out of our colleagues here at Yale and Chicago, thinking about the intrinsic noise resilience of this QRAM architecture. They claim that the fidelity does not scale as badly as people thought. In other words, if you have a memory capacity of capital N, even though you have involved capital N number of qubits and the circuit depth is log n, the error scaling does not scale as the number of possible error locations in the circuit, which should be n log n. It actually scales much better, much more friendly. It's log n squared. The intuition, I won't go into the proof of this paper, but the intuition is that if you're accessing this part of the memory, error that happens to the other part of the tree doesn't affect this entangling operation. And when you compute the fidelity, the error only affects the subtree rooted at that error. So the error is localized, and they were able to show that because of this locality of error, the effect of the error is localized. For the fidelity, they can derive this scaling of error. Epsilon here is the probability of error for each qubit or gate. And then what we are interested in is to improve this scaling, because for large n, this is still pretty bad. One seemingly straightforward approach is to apply error correction, and suppose you can correct any single qubit error, and the remaining dominant error is 2 qubit errors that happens with probability epsilon squared. Then you can potentially reduce the epsilon to epsilon squared, and getting this scaling much better. The challenge, though, is that in order to correct single qubit error during the query process, you have to implement fault-tolerant gates. In other words, you don't want to let the gates during the query propagate single error to 2 errors that you couldn't correct. So you need to implement fault-tolerant query operations. And the operations, as we mentioned, involve plenty of control swap gates. And control swap gates happen to be non-Clifford gate, which is very difficult to implement fault-tolerantly. What we want to see is that is there something special about QRAM that will allow us to implement the control swap operation fault-tolerantly. This is an unpublished result, but I'll mention some of the high-level takeaway But we hope that we will release our paper early this year. So today I'll just offer some of the high-level intuition of what we are thinking about. So now we're thinking about control swap operations. It's a non-Clifford gate, but it's very sparse. If you write down the matrix representation of the control swap gate, there are a lot of entries that are 0. It doesn't immediately tell you how easy or difficult it is to implement the gate fault tolerantly. But if you look at the possible input state associated with these operations, so in other words, the input to this operation C swap is restricted, right? It's not, you don't need to implement a C swap that acts on any arbitrary input state. You only need to implement a C swap gate that acts on the valid state or the state that has an error that can be corrected by our error correction code. And there are only a few valid states, valid inputs to the control swap. In other words, there are only a few columns of this C-swap gate that you need to care about. And when you look at a single column, it's really sparse. So we are able to show that without going to the proof of it, that we can implement fault tolerance C-swap operation with respect to erasure error, single qubit erasure error, using the four qubit error detection code to encode each physical qubit, to encode each logical qubit with only 4 physical qubits. You can, in fact, correct single qubit erasures. So even though 4 qubit code is an error detection code, with respect to erasure error, you can, in fact, correct them. What's more, we were able to show that we can implement fault-tolerant control swap gate on top of the 422 code. Surprisingly, so this is a really surprising result because fault-tolerant C-swap gate does not exist for 422 code. But when you consider applying C-swap on these particular input, we can show that it's fault-tolerant. So it's really thinking about an application-specific implementation of the fault-tolerant gate that I don't think people have paid enough attention to. So if you only care about running your C-swap gates inside of a QRAM operation, you don't need to build a C-swap gate for arbitrary input state. That's the main observation or takeaway from our work. Without going to too much details, we were able to use that technique of fault-tolerant C-swap gate specific for QRAM to reduce this epsilon to epsilon squared. And then we also able to use further use the structure of the circuit, which is very symmetric, to further reduce the log squared n scaling down to log n. And with this new scaling, it's much better asymptotically than the scaling that we begin with. Okay, so this is sort of my high-level overview of why I think people want to think about implement error correction tailored to specific applications. For us, the application is QRAM. I'm gonna skip this part because I think I'm short on time. I do want to talk about my second effort related to magic state bottleneck. Um, so when you think about error correction, there's another bottleneck that we have to address. In particular, it's related to what I just mentioned earlier about the difficulty of implementing non-Clifford gate fault tolerantly. There's a theorem called Easton-Keneal theorem in quantum error correction that no code can have a universal transversal gate set. So transversal gate is a set of is a technique for implementing a logical gate using in some sense bitwise operations so that a single error will not propagate uncontrollably to multi-qubit errors. That's a desirable implementation. Because it's a local bitwise operation, it's easy to implement. But unfortunately, for a single code, we cannot implement a universal gate set using only transversal gate. To overcome this limitation, the leading approach is still to perform something called magic state distillation. Before I mention how a magic state distillation is accomplished, I just want to motivate how bad this is, how costly or expensive it is to perform magic state distillation to overcome this. So take application, for example, that require, let's say, some non-Clifford gates that doesn't have transversal implementation in surface code. Take T-gate, for example. If you need to perform fault-tolerant T-gate to some precision, we typically need, for example, 2 rounds of distillation, which is, let's say, using the leading protocols for doing that. I'll mention what that is in later slides, but if you consider this reasonable operation for achieving fault-tolerant T-gate, then for the application, I forgot to mention what this application was. For the application of quantum simulation, it typically involve, in fact, involve millions of T-gate or non-Clifford rotation gates within the algorithm. If each T-gate require some distillation operations, then you are looking at more than 98% of the operation will be spent on just distillation alone, and the rest doing actual computation takes only 1.3%. So this is really a bottleneck. The cost for distillation is so high that any improvement in distillation will, in fact, improve the overall algorithm significantly. So this is the earlier work that this number, this counting is from my earlier work. In that work, we were talking about, again, embedding the distillation in a 2D nearest neighbor architecture, and we think about how to implement them efficiently. But today, I want to mention our new technique developed last year of thinking about again, tailored to the application of magic state distillation, how you think about some cheaper ways or more efficient ways to implement these circuits. Okay, so this is the high level overview of what magic state distillation is doing. The idea is that you want to prepare some quantum state, a specific quantum state with high fidelity. And you can do that by first preparing multiple copies of the state with not so good fidelity. And then apply some kind of error detection, filtering, or error correction process to construct better fidelity magic state from those noisy ones. After you have prepared this good magic state, you can then use that state to perform the logical gate through a process called gate teleportation or injection. This is the circuit for doing that for T-gate. If you have a good fidelity T-gate plus transversal implementation of transversal gates and measurements, then you can implement the logical T on the qubit with high fidelity. This is the idea for how to get away with Easton-Conneal theorem using high fidelity magic states. So overall in the computation, then it will look like at different point in the computation, which involve many Clifford gates implemented transversally. Occasionally, you will input your high fidelity magic states at different point of the computation. In order for this computation to be done efficiently, you need to supply the magic state at a rate that demanded by the computation. So you need to be able to provide large number of T states with high fidelity efficiently. So there are many approaches for doing that. What I want to motivate here is a post-selection based approach that we developed last year. Why post-selection? The motivation is that you are doing state preparation of this magic state. So if you failed, you can afford throwing that away, right? So you're not performing computation, you want to be right from the beginning to the end. You can afford throwing away bad shots. So when you think about state preparation, post-selection approach or probabilistic approach might be easier or incur lower cost. So that's our motivation. And it turns out that we can, in fact, implement logical non-Clifford rotation probabilistically very efficiently. The idea, the high-level intuition of why rotations, for example, small angle rotations can be implemented this efficiently is that if you look at a block sphere and the state that you want to prepare is sort of a rotation applied to the plus state. The plus state, let's say, is sitting at the x-axis. If the rotation angle is small, then it's really close to the plus state. And this inscribed double pyramid is called the octahedron. Inside of the block sphere is where you can get using Clifford gates starting with the 0 state. Here, it's a non-Clifford rotation, but it's close to the Clifford state, plus state. And when it's close, you can really approximate it in the neighborhood probabilistically by sometimes preparing the X state, sometimes preparing something non-Clifford. So some approximate or probabilistic approach might be straightforward since it's close to the Clifford state. Okay, so that's our main idea, and our construction is very simple. You identify the logical Z operation, let's say for a surface code, and the rotation you want to accomplish is the logical rotation, which is defined this way. Replacing the logical Z with this physical Z operation for the surface code, we can, in fact, perform physical rotations on these qubits supported by the logical operation. And what accomplish is the 3 sequential rotations on the 3 qubits. If you expand each of the rotations, you will see that the desired term shows up, but also some other terms that we don't want. And it turns out these other terms are combinations of I and Z from this product expansion, is a single Z or 2 Z terms. And for surface code, distance 3 surface code, they are exactly the error terms. So in other words, we can in fact project the quantum state using the the syndrome measurement in the surface code to project the state into exactly this desired subspace. So after the physical rotation plus projection, we can implement this logical Z operation. Of course, it's a syndrome measurement conditioned on projecting to this particular subspace. When you measure, your measurement result is non-trivial, meaning that you observe error, then you are projecting to some other states. But the naive strategy for us is to throw away any shots if you detected any error. Okay, so notice that here we're not detecting errors. We're sort of rotating the qubits, which is like purposely injecting error into the system and let the surface code perform the standard error detection. And if it says I have detected an error, then we throw it away. What's left over is the desired logical rotation. So we can derive what the logical rotation angle is based on the physical rotations. And also we can derive the success probability. I'm going to skip the details again. You can look at the paper for more details, but we have done the error analysis to understand what would happen if error happens during this operation. We can also benchmark how the success rate of this process. It's a probabilistic operation after all. So it has failure rate associated with it, and how well we perform, how much fidelity we can improve using higher distance code, or how to quantify the success probability. Notice that our solution have decaying success probability for larger angles. So what we found is that for small angle rotations, our scheme is has high success probability, hence should be used radically. So the takeaway, without getting into the details, the takeaway of our strategy is that if you think about magic state preparation or distillation, it's a state preparation process. Probabilistic approaches should be considered because you can afford throwing away bad shots, as long as your success rate is not too low. And what we found is that if you are willing to sacrifice some success rate, you will be able to reduce the cost of preparing that magic state with orders of magnitude with fewer gates. So that's the takeaway from that study. So with that, I think I'd like to take questions and also acknowledge my collaborators and funding agencies. And thank you everyone for your attention.
Thank you so much, Professor Ding. Yeah, that was a fantastic talk. Yeah, so if anybody wants to just unmute Shantanusan, I see you have your hand raised. Yeah, you're welcome to ask your question. Other people afterward, you're also just welcome to unmute and ask.
Thank you, Professor, for this wonderful presentation. I learned a lot today. I have a few questions. They might seem quite foolish to you, but I didn't understand, like when we discuss about the probabilistic approach, we saw the graph for different rotation angles and the level of error there. Is there any correlation between the more number of such predictions we make and the overall error we get in the sample, or it is not related to the sample size?
Right. So you're talking about uh, dependence of our approach on input error rate, if I understand the question.
Uh, More so as the number of inputs, like how many inputs we are giving to this
Right.
model.
So yes, I don't have the plot on the slides, but it is included in the paper. We do need to use multiple copies of state to overcome the success rate, right? So if you have to throw away things, we have to repeat until success. So you need to pay the cost of preparing multiple states. But this distillation process involve inputting multiple states, performing distillation and output fewer number of higher fidelity states. So there you also have sampling cost. So if you're using our strategy as input to distillation, then what's effectively is 1 over success probability overhead in the number of samples for your distillation. But the gain from our strategy is that your distillation input fidelity is going to be a lot higher if you compared to you didn't use our scheme, and then potentially you will need fewer rounds of distillation to reach the desired output fidelity. In other words, you will need fewer number of samples because you have started in a better place. And overall, we are able to show that that saving in the samples can compensate the overhead of the samples from the success rate. And the most comprehensive counting of overall cost end-to-end from multiple distillation or applications of the different rotation angles is included in the paper. So you're welcome to check it out.
Thank you, sir. I definitely will check it out.
A very good question. Thanks.
Yeah, if you anybody else who has another question, feel free to unmute or raise your hand. In the meantime, while you're thinking about that, I definitely have some of my own as well. So I was going to ask, you mentioned that there's a like redundancy in QRAM that allows you to do additional syndrome checks. Could you elaborate on that a little bit?
Yes. So let me go back to the slides where I said that. So information in the QRAM is stored in a entangled and non-local way. What I mean by information stored is that as input to the QRAM, you have the address bits 0, 1, 0, for example. After you have loaded that address bits into the tree, it's not only stored in the qubits of the that stores the address, but also in the location of the qubit as well, because you have routed the address qubit either to the left or right, depending on the value of the qubit. So you have created redundant information about the address. And we were able to sort of leverage that redundancy, compare the value of the qubit with its location to know whether an error has happened. And this is the source of our improvement in the scaling. To give you a concrete example, if the first address is 0, then the address is going to load in the root as a 0 state. If the second qubit address qubit is 1, it's going to be written in the left child, not in the right child, because of the 0 in the first qubit. And I can check if the 0 state is consistent with the left child being in the 1 state.
Yeah, wonderful. Thank you so much for that answer. Yeah, so I was also going to ask you, so you were talking about correcting for erasure errors, and I wanted to ask, like, how much of a difference when you're designing these like algorithm sensitive quantum error correction does having bias noise in the processor make? Like, if you think, like, if you have a quantum processor that's more prone to dephasing or relaxation errors or erasure errors, like, do the bounds change appreciably, or is it just like a small overhead for different types of errors?
There's definitely room for exploring this fault-tolerant implementation of QRAM with respect to different types of error profile. What we were able to show is the simplest example of erasure error. We are able to implement with very low cost of encoding, just the 422 code, that you can correct the erasure. If you have, for this particular example, using other model on the 4-qubit encoding, we were not able to achieve the same scaling as the erasure error model, partially because the erasure error is a particular type of error that's easy to correct or easy to analyze for fault-tolerant gates. But I can totally see future exploration on using maybe a bit more redundancy in the encoding to and then also take advantage of symmetry or information about bias in errors in the qubits to achieve the same or even better scaling than we can. For example, maybe with because the redundancy in QRAM is may complement with let's say bit flip errors and bit flip codes, you might want to have let's say asymmetric surface code that corrects phase error purely from the encoding, but correct bit flip errors with a combination of the intrinsic redundancy in QRAM plus the encoding itself. So that's a part of what we discussed in this paper last year about using asymmetric surface code plus the error correcting capabilities within QRAM to achieve larger distance error correction.
All right. I guess unless anybody else has any other questions, maybe one last thing that would be interesting to ask, just because it relates to one of the QRISE challenges. So IBM's QRISE challenge involves exploring these dynamic circuits that include measure and feed forward. And I wanted to ask if, so there's this example of that you use this quantum teleportation type circuit where you use this active feed forward, or at least the way I'm interpreting it, to do quantum teleportation. How, like, do you think when mid-circuit measurement becomes more like widely available in quantum platforms, like do you think this like will lead to meaningful speed ups in some of these algorithms? Can you see this being an important tool?
Yeah, absolutely. What I didn't draw here, but Ben, you pointed out, is that these measurement results will be used to feed forward to perform some kind of adaptive operations to accomplish this teleportation or entanglement swapping. So indeed, we need capabilities of mid-circuit measurement and feed forward to actually realize what I mentioned here. And I think this also highlights one of the advantages of using mid-circuit measurement and feed forward to overcome connectivity constraints. If you have nearest neighbor interactions, purely unitary operations, then you will incur typically larger overhead to communicate qubits within an algorithm than you can with teleportation. For our example, it's required to preserve this log scaling in QRAM. Otherwise, this unitary approach is going to break the logarithmic depth scaling. I can see future directions in understanding the need of entanglement distribution or long-range communication within an algorithm. If there's an algorithm that needs to communicate remote qubits, then potentially with mid-circuit measurement and feed forward can accomplish that communication a lot more efficiently. So that's at least something I know that feed-forward measurement can help within an algorithm. But I think this is a very timely research direction, as these quantum hardware such as IBM provides a test bed for these new capabilities for us to try different algorithms, and I can see better understanding of how to leverage this in an algorithm once we try them out. So I'm intrigued by the fact that this is one of the QRISE challenges.
Thanks for that great answer. I'll just give like 5 seconds in case anybody else feels like unmuting and asking a question.
Hi, Professor. Thanks for the talk. So in an earlier slide, you mentioned that the error is localized to the subtree.
Yes.
I was wondering whether the error could like instead propagate up to the parent. Like, why is it localized to the subtree?
Right. That's a very good question. It will be more involved to explain, but you can check out this paper, which first discovered this local error property. But the high-level answer intuition, high-level intuition is to consider sort of what the operations are doing. So, and the error model. So if you are performing the sort of okay, so so there are two so this work discovered how errors are localized for generic errors, and our work that I referenced showed that we can modify this QRAM structure to even to also localize errors, but just for bit flip errors. So our gain is that you can have more parallel access. But if you are referring to this work, then the intuition is that my gate will involve swapping the data of your root to the left and right child. But if this address qubit is wrong, then you're gonna swap to the wrong subtree. But the information that's got swapped up is sort of it's not storing our data. So usually you are routing the data from the root of the tree downwards. Because of this directional information flow, errors will not propagate up in this tree. But the actual analysis has to be more rigorous than that. There are cases where error will propagate up, but it will not contribute to the fidelity loss. And so I encourage you to take a closer look at this work to understand the behavior more rigorously.
That's interesting. Thanks.
Could I just add a little bit to that question? Yeah. So I guess somewhere in the middle, you also mentioned like we are performing the error correction even between two states. So does that mean like we are checking for errors between two levels of this branch, or?
Yes, exactly. So we are comparing values between different levels in order to use the redundancy within QRAM to correct for errors.
Got it. Yeah.
Okay, well, we've already kept you a little bit over time, but thank you so much for taking the time to stay and answer some of these questions. And thank you for your talk, especially and the thoughts you shared and the very interesting directions it seems like in this rich field. Yeah, so to everybody else, the next talk in just logistical stuff, the next talk in the QRISE speaker series will be given by Jesse Barasowski next Friday, April 5th. And as a reminder, the submission form for projects will be released on April 8th, and project submissions are due at midnight Eastern on April 12th. Yeah, so thank you everyone so much for joining us, and thank you again, Professor Ding. If you have any questions, feel free to reach out to us directly, and we'll see you next week.
Thank you for having me.
Thank you, sir.